a new managed database service, which gives you a distributed, relational SQL database alongside the distributed NoSQL databases that you already know and love in Cosmos DB.
Yeah, so for the next 2 hours, we're going to dive into this new managed service that we have for Postgres in Azure Cosmos DB. We have a series of short technical sessions. You get to learn key concepts with how to do demos, and you'll get ready to start all, quickly.
We're going to start with 2 sessions back to back, and then we'll come back and you can check in with us before the next group of technical sessions.
Yes, and during this event, the speakers and our teammates, are going to be live to answer your questions. So please feel free to use the chat throughout the event.
And if you miss any of today's sessions or you want to come back and watch them again at half speed, at 2x speed, you can catch them all at aka.ms/Liftoff.
Okay, let's get started. Our first session today is with the General Manager for Azure Cosmos DB, Kirill Gavrylyuk, who will give the keynote for today's event. And then we have our Principal Software Engineer Manager, Sai Srirampur. He's going to talk about how you can model your data for distributed Postgres.
All right, let's go.
Yeah.
Thank you, Claire and Iria. Hello everyone, I'm Kirill Gavrylyuk, General Manager for Azure Cosmos DB and Postgres. Welcome to our show, Liftoff. Today we have some exciting news to bear. Let's take a look at our slides. It has never been a more exciting day to work with data. For a long time, we've been using relational databases with our apps, right? They are great. They provide asset guarantees. They have really simple but rich SQL language. But sometime around 2010s, applications started to feel that pressure on scale, performance, the ability to change data shape fast, that relational databases were not quite set up to do. NoSQL databases emerged, including our own Azure Cosmos DB, launched in 2016. It is now everywhere. No matter what you do in your daily life, whether you're ordering a cup of coffee from Starbucks, whether you are buying something from your favorite online retailer, Walmart or any other, or whether you go check in to an airline, check into a hotel, you're using Azure Cosmos DB. Even if you're remote into a meeting using your favorite meeting tool, Cosmos DB is everywhere. It is trusted. It is known for its reliability, performance, limitless elastic scale, ability to bring data anywhere in the world thanks to global distribution, and 5/9 availability. Now, come 2020s, those exact same pressures that brought to us Azure Cosmos DB and other NoSQL databases now impact apps everywhere, including those apps that really need asset guarantees and that richness of SQL language. This is exciting times where relational databases and NoSQL databases are converging. And today, we've just announced our new baby in Cosmos DB family, Azure Cosmos DB for Postgres. You can go to Azure portal, create Cosmos DB account, and among the familiar APIs, NoSQL API, Cassandra, or Mongo, you can also choose Azure Cosmos DB for Postgres. That brings you the power of Postgres. This is Postgres engine. As is, it is not a simulation, but it's combined with limitless elastic scale and global distribution and high availability of Azure Cosmos DB. Let's take a look. We can create Azure Cosmos DB for Postgres. We can now use, once your account is created, you can use any of your familiar Postgres tools. Again, this is Postgres engine. There is no simulation there. 100% Postgres. You can use any of your Postgres features. You can bring your favorite Postgres extension. It just works. You can start small with a single node, but over time, your application likely will grow. You will need that scale, that performance, and you probably will need to scale out. And Cosmos DB for Postgres allows you to scale out to arbitrary number of nodes, and over time, we'll make it automatic, so you don't even need to go to the portal and click it. Now, to take advantage of that scale out, you need to go back to write a simple command that's pick a table that needs that scale out and shard it. Create a distributed table. It's one line, and with that line, you can execute it on your production database. We borrowed exactly the same technique from the underlying Cosmos DB to bring you this scale out as a synchronous, non-blocking, has no impact on your application performance, but you can now scale out your workload to multiple nodes. Now what will happen is that your traffic will get distributed across those nodes, and if you picked a good shard key, it will probably distribute more or less evenly. But over time, it just happens that one of those shard keys will probably start to get big. If you're, for example, building a multi-tenant application, one of your tenants become more successful than others and become big. And Azure Cosmos DB, just like with NoSQL APIs, allows you to redistribute those tenants. And so we can move transparently to application. We can move this tenant to a separate node. No impact. It's a synchronous separation. No impact on your production database. But now your tenant is on a separate node, isolated, does not impact any of your other tenants, and can take advantage of more capacity. These are just examples of what the elastic scale out of Cosmos DB for Postgres brings to your Postgres application. Now, just like with any other Azure Cosmos DB API, Azure Cosmos DB for Postgres brings you global distribution. You can go ahead in the portal and add a region. And now your Postgres database is replicated across multiple regions. It allows you to bring the data to where your users are and take advantage of low latency. It also allows you for high availability for your application, so you can dynamically fail over to another region should a rainy day hit. These are just few things that you can do with Azure Cosmos DB for Postgres. Stick around for our show. Enjoy it. There is a lot more exciting discussions is going to happen. We'll show you some few really cool things. You can go to AKMS Try Cosmos DB and take Azure Cosmos DB for Postgres for a spin. You do not need Azure subscription. You do not need your credit card. You can take it, try it, build an app with it. I'm really excited to see what apps you're going to build with Azure Cosmos DB for Postgres. Enjoy the show.
Hi folks, I'm here to talk about how to do data modeling for distributed Postgres in Azure Cosmos DB. I'm Sai Srirampur and I lead the customer engineering team for Azure Cosmos DB for Postgres. Before we get started, let's understand what is Azure Cosmos DB for Postgres. Azure Cosmos DB for Postgres is Azure's fully managed distributed SQL offering built upon the core benefits of Postgres. It stays native to Postgres, supporting the latest versions and the rich features, including JSONB data type, extensions like PostGIS, rich indexing, and so on. It is powered by the fully open source Citus extension to Postgres for distributed scale. To achieve distributed scale, Azure Cosmos DB for Postgres extends Postgres with the superpower of distributed tables. You can start small by building your apps on a single node, the same way you would with Postgres. As your app scale and performance requirements grow, you can seamlessly scale to multiple nodes by transparently distributing your tables. Create distributed table concurrently is the magic function that Cosmos DB Postgres provides to distribute tables across multiple nodes. Distributing tables to scale out to multiple nodes is all online. Reads and writes can go through as usual. That is, your app would have no impact when you distribute tables and scale out. Let's learn more about what distributing tables actually does under the covers. In a multi-node deployment, there are two types of nodes. One is the coordinator node and others are worker nodes. Coordinator node and worker nodes are nothing but simple plain Postgres databases with the Citus extension loaded. Your application connects to the coordinator node and interacts very similarly how it does with Postgres. The coordinator node is responsible for distributed planning. The worker nodes are the nodes where the actual data exists. That's where the actual computation happens. To distribute a table here, as an example, I'm distributing the campaigns table on the company ID using the create distributed table concurrently API. Once I run that command, the coordinator decomposes the campaigns table into multiple shards. Shards are nothing but simple plain Postgres tables that are on the worker nodes, which hold a subset of your data. Here, they would basically hold a subset of your companies because I'm distributing the campaigns on the company ID. When I run a query for a single company ID, the coordinator node automatically routes the query to the right worker node where the company exists and executes the query. Whereas if I run a query that spans across companies, the coordinator node parallelizes that query across multiple nodes, pushes the work as much as possible to the worker nodes, and does the execution. So if you see, distribution column lies at the heart of how Cosmos DB Postgres efficiently distributes data and executes queries. Choosing the right distribution column is an important step to effectively use the database. Here I have a slide that shows why distribution column, also called shard key, is so critical. First, shard key dictates the performance and scalability of your application because your data and queries are distributed based on that shard key. You don't want to pick a key that causes queue across the nodes, right? Because it won't be optimal for performance. Suppose I pick a column which represents 50% of the data, then I would basically get throttled or bottlenecked on a single node. You don't want to pick a key with low cardinality. Suppose I pick a column which has cardinality of 2, say I pick a Boolean column, right? Under the covers, you can scale only up to 2 nodes because the cardinality is 2. So you want to pick a column which has higher cardinality, mostly at least like in thousands. You want to pick a key that optimizes joins in your queries. So joining 2 tables with different shard keys can be slow, right? So you want to choose a common shard key across large tables. I'll do a drill down into this particular bullet point later in the slide. A column that incurs query parallelism is not always great. It is not optimal for transactional workloads because a query fan out is costly. It can cause network latency. Rather, you want to pick a column that routes queries to a single node. Whereas in analytical workloads, you want to pick a column in a way that your queries are parallelized across multiple nodes. So in summary, distribution column is a very important concept in Azure Cosmos DB for Postgres. Assuming that we have understood how Cosmos DB Postgres distributes data, let's learn 5 tips for distributed data modeling with Postgres. First is column that adds natural dimension to data is a good shard key. We have seen this across customers where if they pick a column that represents the central piece of the application or lives at the heart of the application, most of the time it works out very well. Some good examples are, suppose you're building a SaaS app, right, where you have multiple customers and each customer interacts with their own data. Customer ID is the natural dimension, or it's the central piece of the application, and it can be a good candidate. Whereas I have an IoT app where, I get data from devices, I analyze this data coming from devices, device ID, which is the heart of the application, is a good candidate. Here I have another example. Say I have an application which analyzes events on GitHub, and these events are actually generated by users on GitHub, right? In that application, the data model is pretty straightforward. I have the events table, I have users table, and I have a dimensions table, which is countries here. Events and users are application specific tables. That's where, application data is stored, and countries is a small dimension table, right? In such application, user ID is a good candidate for distributing tables. The reason is because it is the central piece. Events are in fact generated by users themselves, and it adds natural dimension to the data. Right, so user ID is a good pick for such a use case. The second tip I have is collocate large tables and make small tables reference. In the GitHub events example, if you see, I have the events and users table, and these are, as I said, the larger tables as they store application specific data. To collocate both these tables, I'm distributing them on the user ID. So if you see, the create distributed table concurrently has the user ID as the distribution column for both the tables. The countries table is smaller dimension table that is shared across users. So I can make the countries table a reference table. And in the Azure Cosmos DB for Postgres world, a reference table is a table that is replicated across all the nodes. I have talked so much about collocating tables. What does this actually mean and how does it help? if you see, I have distributed users and events on the same column, which is user ID, and this makes them collocated, which ensures that data for same users for both the tables is on the same node. This helps optimally perform SQL operations like joins and foreign keys in a distributed environment. For example, I do a join between users and events. That particular join, as you're seeing on the screen, can be pushed down across the shards directly to the worker nodes. So this would give you great performance because the join is very efficient. For countries table, as it is replicated across all the nodes, it can directly join with the users table, and that join also can be pushed down. Hence, collocation is a very important concept, and this tip suggests that you want to collocate large tables by distributing on the same column and make the smaller tables as reference or replicated tables. The third tip I have is use JSONB data type to store unstructured data. Azure Cosmos DB for Postgres natively supports the JSONB data type, and it helps you store semi-structured and unstructured data. The advantages are you have a simplified schema. So you can have a single table to store a variety of data. Say I have GitHub events data, and if you see I have the payload, which is the JSONB column, I can store a variety of events in a single table. JSONB data type also has this thing called GIN indexing, and this helps you faster access to the JSONB. So you can search through the JSONB, you can query through the JSONB in a very optimal way. Next, you are basically adding NoSQL and document-like capabilities in a distributed Postgres world. And we have seen this work very well in implementing workloads that need scale. Say you have IoT, events, logs, where there is no structure to data and you want to store that, you basically use JSONB. The fourth tip I have is complement distribution of tables with time series partitioning. So in this example of GitHub events, here if you see, I have decided to distribute on user ID. Azure Cosmos DB for Postgres also gives you capabilities to partition distributed tables. So I can create, a time-based partition. So here, if you see, I have multiple partitions for the GitHub events. I have, partitions which are monthly. So I have a partition for July, August, September, January, February, etc. And Cosmos DB Postgres also lets you archive older partitions using columnar storage format. The newer partitions where you get real-time ingests and where you get majority of the queries are row-based, whereas the older partitions are columnar and they're compressed. The benefits of partitioning are it helps filtered querying when there are timestamp filters. There is efficient expiry because you can basically drop the table, drop the older partitions instead of deleting the data. It also helps efficient archiving of older data. So I'm basically archiving the older data using columnar and saving storage costs. And last but not the least, we have seen this a lot in time series workloads where customers complement distributing tables with time-based partitioning when there is a time dimension present. So the fifth, so here is an example. I mean, the Cosmos DB for Postgres supports, native time series APIs, and I have APIs for automatic data partitioning, automatic data archival, and automatic data expiry. Under the covers, say for automatic data partitioning, by just running this command, it creates partitions in the history and in the present. And for archival, it automatically, makes older partitions columnar. And for expiry, you just run this command. It would basically drop all the partitions that are older than the specified time. So the fifth tip, till now, whatever tips we have talked about are related to schema and table modeling, right? The fifth tip is more related to queries, right? Scope queries to shard keys where possible. So wherever possible, say in a SaaS workload, right? Queries can be scoped to the tenant ID or the customer ID. Make sure to add that particular column in the filter, right? So here I have an example where I'm, updating a table with the ID as the filter. That if you add the company ID filter, as this is a SaaS multi-tenant workload, this would be much more efficient, right? Basically, by this, you're avoiding unnecessary fan out and helping query latency, right? And this is more relevant in transactional workloads where you want to optimize network latency by, having the distribution column present. So just to summarize, these are the 5 tips for distributed data modeling with Postgres. Tip 1, column that adds natural dimension to data is a good shard key. Tip 2, collocate large tables by distributing them on a common column and make smaller table reference. Third, to store unstructured and semi-structured data, use JSONB data type. Fourth, complement distributed tables by partitioning and on time whenever there is a time dimension. This is specifically when you have time series data. And tip 5, scope queries to shard key where possible. If you follow these 5 tips, I'm pretty confident that you'll have a great experience with the product and you'll build scalable operational apps with Azure Cosmos DB for Postgres. Happy testing. Thank you.
And we are back. Kirill always brings so much energy to the table in his talks. You can see that he's truly excited about the fact that there's now a relational distributed SQL database that's part of Azure Cosmos DB. In the rest of today's sessions, we're going to dive deeper into some of the capabilities that Kirill covered in his keynote. Things like starting with Postgres on a single node, distributing tables, tenant isolation, and multi-region replication.
Yes, I really enjoyed Sai's session on data modeling. It's interesting, the tips and the guidance that he shared, how it's this is kind of like similar rules you'd follow with like a NoSQL database.
Well, I suppose that all distributed databases have some things in common, whether they're NoSQL or relational. Sai's tips on how to choose a shard key and how to combine sharding with Postgres native partitioning were super useful. I think his talk is a must-watch.
Yes. Oh, so our next session, we have the principal software engineer, Onder Kalaci, who will talk about, Citus open source extensions that powers Azure Cosmos DB for PostgreSQL.
And then we're going to have a senior program manager, Adam Wolk, who's going to join us and talk about scaling out Postgres in an online way for multi-tenant SaaS applications. And he's also going to cover the new Postgres extension called Azure Storage, which helps ingest blob storage.
Yeah, so okay, now don't forget, okay, our teammates are here to answer your questions, so please drop your questions in the chat.
All right, let's watch.
Yeah.
Hello everyone, my name is Onder Kalaci and I'm a principal software engineer at Microsoft working on PostgreSQL and specifically on Citus. So today I will be talking about foundations of distributed PostgreSQL with Citus. The first question is, what is Citus? Citus is a PostgreSQL extension that transforms PostgreSQL into a multi-node distributed database. From the application's perspective, it is just a PostgreSQL. Behind the covers, Citus hooks into several points in the query processing and can change how the database behaves. And because from the application's perspective, Citus is just PostgreSQL, Citus can be used with all the tooling and all the ecosystem of PostgreSQL. And again, because Citus is an extension, it is up to date with all the new PostgreSQL innovations. As soon as a new PostgreSQL version comes, Citus is ready for running with that version. And then if you are not very familiar with Citus, Citus is an open source project that you can find all the source code on GitHub. So then the second logical question is, what is an extension? Like what does it mean to be an extension to a database? So from Postgres perspective, an extension consists of 2 sets of things. The first thing is any SQL object, like it could be a table, type, function, whatever you name it in a database. And then the second piece is some shared library that can be loaded into Postgres. So on the left-hand side, you see the object, for example, that Citus creates. So there are some tables, some functions, and some other things, but so you can have any SQL object. And then on the right-hand side, you see the C code that actually runs in the shared library and loaded into the Postgres when these functions are called. And this is how Postgres makes extensions work. So PostgreSQL allows extensions to change, to extend, to override how the database behaves. And there are several APIs that enables extensions to do that. For example, as we talked in the previous slide, an extension can define some SQL callable functions. So an extension provides some SQL, and then users can call this in the SQL command line. I think probably the more important parts are planner and executor hooks. So PostgreSQL allows extensions to override how the planning and execution is done on the database. And as being a transactional database, PostgreSQL also allows extensions to override, to extend what happens during the transactions. And like, especially in the critical points of the transactions, like just before the commit or just right after the commit. So when a user comes in and executes a query on the Citus database, Citus just behaves as if it's a Postgres, gets the query from the user's perspective, but under the covers, what Citus does is gets this query and decides where the shards are for this query in the cluster, and then runs these queries across the cluster in parallel. And these queries are, the queries that are sent to the shards are just regular PostgreSQL queries, and the shards are regular PostgreSQL tables. And then from the application perspective, it's just talking to the Postgres database and getting the results back. And as part of being a distributed relational database, Citus also handles distributed transactions. So there are roughly two classes of transactions. The first class of transaction are transactions that touches only a single node in the cluster. For such transactions, Citus delegates the transaction to the worker node where this transaction is running. So basically, Citus's job is to delegate the transaction to the worker node and let the heavy lifting done by Postgres. When there are multiple nodes involved in a distributed transaction, then Citus's involvement becomes a little bit more. So PostgreSQL provides some hooks, as I mentioned earlier in this presentation. So, and then Citus uses Postgres's another infrastructure, which is called two-phase commit, while handling this multi-node transactions. So just before the commit happens, PostgreSQL lets Citus know about that. And then at that point, Citus sends prepared transactions to the remote nodes. Prepared meaning that it is ready to be committed. And once every transaction on multiple nodes are prepared, right after the commit happens on the coordinator, PostgreSQL again gives control to the extensions where Citus goes and commits the prepared transactions. So this is how Citus integrates with the distributed transaction management. And then in this last slide, I also want to talk about Citus 11, like what is the current state of Citus and one important feature of Citus. So in this presentation, I implicitly talk about a coordinator node. So as of Citus 11, which happened around 6 months ago, Citus supports querying from any node. Now you can connect to any node in the cluster and do select, insert, update, delete commands. But certain commands, the DDL commands like alter table, create index, or create table type of commands should still go through the coordinator. And then just to give some more context on this, a single coordinator is already capable of handling very high number of transactions and very high throughput transactions. But then there are some very demanding applications where a single coordinator might become a bottleneck. And more commonly, some users and some prospective Citus users used to see the single coordinator as a potential scalability bottleneck for the future. Although Citus coordinator can handle very high number of transactions, users wanted to have the flexibility to have even higher throughput. And then as of Citus 11, with the query from any node, Citus can scale to really high number of transactions with very high number of writes like in total per very high number of writes per second. And then under the hood, how this happens is that the Citus coordinator holds some metadata and the schema of the cluster. The schema involves like tables, views, functions, whatever you use in querying the database. And this metadata and schema is now synced to all nodes, which enables querying the database from any node. So this is end of my presentation. Thanks for listening.
Hi everyone. With Citus, with this release of Citus, we really put the focus on the ease of scaling out. So regardless, if you start from a single basic tier cluster, which means one coordinator node and no workers, we want to be absolutely sure that you will be able to quickly scale out without any pain points, even if you made some bad decisions or forgot to do some things at the beginning of your journey with Cosmos DB for PostgreSQL. So let's start with a simple table, observations, which already apparently was created by me beforehand. So let's drop it and create it again, just so we make sure I don't have any leftovers from me trying this before. So we have this simple table observations that we'll fill with some data. It's just several fields, tenant ID, measurement, payload, observation time. And we want to put some data in it, but where to get data? And one of the things that we want to ease is not only scaling out, but getting your data into the cloud. So a common pattern of getting data into the cloud is to use a service like Azure Blob Storage to use it as a staging environment or as a target environment for your, for example, IoT devices to write data to, and then directly pull it into your Citus cluster. So we enabled an extension in Citus, which is called Azure Storage. We can see it's already installed in this case. We can see it here. And we can use this extension to operate on existing blob storage containers. And I prepared the container beforehand, which is named PG ABS, which is PG for Postgres, ABS for Azure Blob Storage. And it's a public container. Public is just the container name. Its accessibility level is set to container public because this allows me to access its content without adding any access keys, though you can also do that if you have a private container. So we will use the blob list function from the extension to show every file in this public container, how much space it how much storage it uses, and its MD5 checksum. So calling this, we see that this container has several files. We will be pulling in observations one CSV GZ, which is a comma-separated values file with zip compression, and it weighs in around 11 megabytes of data. So let's pull that in using the copy command, and you can't do this on normal PostgreSQL without the Azure Storage extension. You can install the extension and do it, but with our extension, the database recognizes blob storage URLs and is able to do API SDK calls to obtain the data and directly pull it into your database. So the moment we execute this command, a connection is made to Azure Blob Storage. The data is fetched over the network between the services, decompressed, and ingested into the table itself, so that you didn't have to copy it anywhere beforehand. You just directly ingest it from the blob storage. And you can see that we loaded 3 million records into the observations table. We can quickly show that. we have all the data inside. We can just show some records of it. And we have some random data, or pseudo-random data. And now we can also check the Citus tables. Citus tables shows you the actual distributed tables that the system knows about. And we don't have any. And one of the frequent beginner mistakes, or perhaps not even a mistake if you started in the basic tier and didn't think that you will need to distribute this table because it started out small and you didn't anticipate it. But then you suddenly realize that, hey, I need to distribute this table because I want to scale it out. It needs much more data than I anticipated. So in the past, if you forgot to do that and had a lot of data in the table and tried to distribute your table, then you would end up with a blocking operation. So this call would be blocking. And let's show it. I will open a second connection to the same cluster where I will try to insert some data into the table while I am writing to it. And as you can see, the insert on the right hand is blocked and waiting for the operation on the left connection to finish, and only after it's finished, I'm done. And this means that your application essentially is not performing writes, which might be very problematic from the business perspective. So in Citus 11.11, we introduced a new functionality called create distributed table concurrently. So I will drop the observations table again. Let's close this connection to see some more. Let's recreate our table the same way as we did before. And I will load the data slightly differently this time around, just to show you another API function from the blob storage extension. So here we are doing an insert into select from blob storage blob get, which allows me to fetch a single file. And as you can imagine, this allows us to do some more on-the-fly manipulations of the data. For example, if I wanted to, I could change or cast some field on the fly. And we are just showing it to show you the flexibility in this method. Okay, now we will do the same thing. We will distribute the table, but we will do it concurrently. Let's get some space here and connect to the cluster again and prepare our insert operation. So now I will first show you that this table is indeed has some data in it. So that's the 3 million rows that we saw beforehand. And we use the same thing. So create distributed table concurrently, the name of the table, and the column that we want to distribute on. So in Citus, you have to tell the database what's your distribution column. The value of this column will be then used to decide where the data, based on the value, goes to which chart and on which node. So I'm going to execute this now. And while this is being done, I'm inserting rows in the second terminal. And you can see the operation on the left is still ongoing, while your application can perform insert statements into the table and other modifications. And this essentially means that this is a safer operation that can be done online without a lot of disruption in your business. So let's close this. Now the table is distributed. We can see that there are more rows inserted. So the 3 million that were there and the 20 rows that were inserted during the distribution. And we can also now take a look at the data. I mentioned the Citus tables table. And we can see that now observations is present there. It's a distributed table on tenant ID. It weighs around 311 megabytes because the data we ingested was zipped. So when we pulled it over with the Azure Storage extension, the extension decompressed the data for us on the fly. And let's see how the data looks. We can imagine that even when you did that, some of your tenants might be not very comparable to others. You might have a big company loading a lot of data and a number of small customers that store a fraction of that. So let's look how our distribution looks like here. So by looking at the data itself and grouping it by tenant ID, we can see that one tenant with ID 293 has significantly more records than all the other tenants present in the database. Now we will find the shard ID, the identifier of the shard that this specific tenant is assigned to. And this is shard 1020.093. And now we can look at the shard sizes. So let's see how even the distribution is. And you can see we have a lot of shards. And one shard is standing out at 78 megabytes. And this is the shard 1020.93, as we talked before. I can scroll up to show it. So we can see that's the same shard ID. So we know that this is taking significantly more data. It's skewing the data in into one shard. So how are they balanced per workers? The cluster I am demonstrating on has one coordinator node and 2 workers. So I can do this query to show for each node, for each table, what's the size of the shards assigned to this node. And we can see that the worker 1 is significantly larger than worker 0. So that's one situation where we, for example, would like to take this large tenant, assign him or assign this customer to its own shard, and move that to a new worker or rebalance it either way, isolate it from other customers because this specific customer has larger needs. So we can do this in Citus, and in Citus 11.1, this operation is non-blocking, like created table concurrently. So when we are doing this operation, we will again perform the inserts to the observations table while distributing the tenant to a new shard. So the distribution is now ongoing, and we are inserting new observations. So again, your application can continue to work, serve the business, while we are fixing the problem in our initial architecture, or we are reacting to changing requirements because businesses change and this client might have changed its usage patterns recently. So you were not able to anticipate that. Okay, so now the tenant is in a new shard and we have the shard ID provided to us. Let's reclaim some space so we can see more. And we can look again at how the shard sizes are. And this is the new shard, 1021.10. And let's confirm that it matches with the one here. Yes. So we can see that this specific shard is now 74 megabytes. Now, nothing in the distribution itself changed between the worker nodes because we just moved the client to a new shard. We also would like to do something with the shard. So let's look at the balancing again. So we see there's no change here. And let's run the rebalancer. Before Citus 11.1, you had to maintain a pSQL connection to the cluster, run the rebalancer, and wait for it to finish. Now, with Citus 11.1, we introduce a new API and essentially a new framework of running jobs in the background that you can simply kick off, quit, and connect back to your cluster, and it still would finish. You don't have to keep this connection open. And as you can see, we have this new pgdist background task and pgdist this background job tables, which we can use to look at the running jobs. So let's look at the second job as we are suggested here by the hint. And we can see that, hey, we had job ID 2, task ID 2, started by Citus, it's done. And it did a shard placement. It moved one of the shards to another node. And we can look at the shard placements between the nodes. So we knew it was 69 megabytes on worker 0, 151 megabytes on worker 1. Now it's a bit more even. It's 73 megabytes on worker 0, 146 megabytes on worker 1. Now it won't be perfectly even because there's no way to move. The sizes of the shards doesn't allow a perfect split in this case. But if you added more nodes, the data could be more evenly spread out among the other nodes, or you can use some other Citus features to move the large tenant to its own node. And that's not the only thing we did with Tree Balancer. By having it run in the background, it's more reliable. It can restart on database recovery. It's faster. We spent a lot of time to improve its performance. And it's there to serve you as best as it can. And without anything more to add, thanks for watching my demo and have a great event.
And we are back. We hope you enjoyed Onder's talk about distributed Postgres with Citus, and Adam's talk too on how Postgres for Azure Cosmos DB for Postgres is a great choice, especially for like multi-tenants and multi-tenant scenarios. Yeah.
Well, I work on the Citus open source project, as you know, and so I'm totally biased. I love how Citus enables people to use Postgres at any scale, from a single node to a large distributed database cluster. And it's still Postgres, and it's all open source. So also one of the side benefits that you get when you're using Azure Cosmos DB for Postgres is if you use Citus open source on your local desktop, you get that functional parity between your local system and what you're running in the cloud.
Yes, I also really like the new Azure storage extension to Postgres that Adam showed. It really works well with like Azure Blob Storage. And I really like also, I think what's really cool is the fact that you're able to copy your data from Blob Storage to Postgres. That's really cool.
Well, and the new Create Distributed Table Concurrently feature that Adam demoed is pretty powerful too, because you can now distribute your Postgres tables and do it with zero downtime in an online way without blocking writes.
Yes, I know we've been saying this over and over again, but really don't forget, okay? We're here to answer your questions throughout the rest of this event. So please ask your questions or to interact with our engineers, in the chat. Yeah.
So next up, software engineer Joe Nelson is going to talk about building SaaS apps using the Django and the Rails ORMs while providing high performance and ensuring tenant isolation.
And then we have software engineer Sudhanshu Vishodia, and he will join us to talk about building IoT applications using JSONB with time series data. So what? Let's
do it.
Yeah.
Hi, my name's Joe Nelson. I write the documentation for Azure Cosmos DB for PostgreSQL and for the open source Citus Postgres extension that powers distributed query execution. We're going to be talking about doing queries more easily, multi-tenant SaaS apps using object relational mappers. So I guess the first most natural question is, what is an ORM? So object relational mapper allows developers to query the database using their native programming language rather than going directly to SQL. So these ORMs are available in pretty much every application framework. Got Django and Rails over there on the side. And to give you an idea of what that means, writing it one way versus writing it another, first we have a select count star from users. That's the plain SQL way to count a table of users. And then we have the way that the Rails active record ORM would express it. You just say user.count. And so that can be attractive because it's shorter for people. In some cases, the queries are shorter. And then the second part is, now that we've talked about ORMs, what is a multi-tenant application and query. Azure Cosmos DB for PostgreSQL excels in several use cases. One of them is the multi-tenant use case. And what that looks like is generally SaaS applications that hold data for multiple businesses that we call tenants, and then it isolates the information from one tenant to another. So we talked about one part, the ORM part. Now let's talk about the other part. What are multi-tenant queries and what's a multi-tenant application? So Azure Cosmos DB for PostgreSQL excels at many use cases, and one of them is the multi-tenant use case. What does that look like? A SaaS app can often hold data for multiple businesses, and we'll call them tenants. And then they isolate each tenant's information from each other. So you could think of an Etsy or a Shopify. You're hosting storefronts for multiple merchants. When you're on one person's store, you don't want to be seeing products from someone else's store. Like, everything needs to be separate. And then individual tenants will query for their own data only, obviously. That's what we want to ensure, not the data of the others. And we say the queries are filtered to a specific tenant ID, so like a store ID. When we're writing for this use case, the multi-tenant SaaS use case with our ORM, really looking for two big goals. One is it should be safe. That is easy to automatically scope those queries to tenants. There's no leaking from one to another. And that it's fast, that the generated SQL, when you write those ORM statements, it creates SQL code. The code that it creates should work efficiently with Azure Cosmos DB for PostgreSQL. And you might think that is easy, it's just standard SQL, but there are some things to be aware of that are specific to being in a distributed SQL database. In this case, it requires some special modeling and query techniques to maximize that query performance. This form of a database actually uses multiple machines, nodes, and those nodes work together to process your SQL. They all will do their part and kind of combine the results to go faster. But it's sensitive to small changes in the SQL itself. And combine that with when you're kind of behind an ORM, it's generating that SQL for you. It's difficult to make those customizations sometimes. You're hiding behind that higher level interface. So we need something to bridge the gap. But we've made our two libraries, so far just two. One is for Django multi-tenant. One is for Rails, active record multi-tenant. And they allow you to write code in a way that you normally would, but translate your queries, the SQL that's generated, to fit really well with that distributed data. So let's check it out. We'll jump right into it. We're going to look at a simplified schema for managing stores, products, and orders. And I say simplified because in this little dream world, shoppers can purchase only one product per order. And we do that just so that the relationships are simplified, because it's kind of irrelevant to the understanding the concept of the code. So we're going to jump into the gray nondescript world of code here. We've got the three tables: stores, products, and orders. And we don't have to look too closely at each of these columns. This is just a data set that I had at hand and it seemed convenient. But we should make take some notes about it. One is, beneath each of the create table, we're running a function called create distributed table. That's what takes the table, breaks it into what we call shards, smaller sets of rows, and those shards get put onto the individual node. Each shard is stored in a single node, and another thing you'll notice is that the uniqueness, some of these primary keys are composite, because as a property, there's too much overhead in a distributed database to maintain or enforce uniqueness across machines. So in this case, the uniqueness is enforced at best per store or per tenant. Just a detail to be aware of. If we look at the way you would code this thing, we saw what's inside the database. And this is just the basics to tell Active Record what it needs to know about the data so that we can use Active Record's form of querying its own language to do it. Here we say, look, we have a store, product, order, just like before. They're all Active Record models, and we kind of declare the way they rely and depend on each other. That stores have products and orders, or that orders belong to products, so that there is a product for orders. And then we declare the primary keys, which you'll notice are slightly different than I said, but we'll kind of correct that later. Okay, given we've kind of put the data in the database, we've told Active Record, generally these are the models we have to work with. Let's use Active Record to make some queries. And I thought a nice query would be, let's find a product the product that's responsible for the most expensive order in a particular store. There's a lot going on in this slide. I'll just break it down. So the first line we have is a command in Ruby. We're saying, take the first store that you find and call it S. It doesn't really matter for this example which one. And then we see the result of that. It's found store ID 1. Its name is store A. There's a date that was associated with it at the time the data was created. And then we see the SQL that active record generated because of that query stored at first. It's essentially saying, give me all the stores, order them by their ID, give me the smallest ID first, and take one of those. Okay, so we've got S. And then we ask active record, okay, of this S, give me the orders, and then find the one with the highest value, the highest sales value. And this is sort of an unfortunate play in words here. We're saying orders.order, that just means order them, like sort them by the value, and get the most expensive one, and then find the associated product for that order. And you can see the result of this is a product. It has product ID 7, has a name, it's a MacBook Pro laptop. And I guess for in this case, there was an order which had a big batch of laptops, so it was an expensive order. As a result of doing this one command in active record, the active record is actually creating 2 separate SQL statements. Now with some trickery, we could probably make this more efficient and make it generate only one. But this is still a really good example of how it's generating queries and the considerations of how it's doing and what we should do. First query it's doing is it's getting all the orders for the current store, and it's sorting by the most expensive one, and it's grabbing that one. With that in hand, it has the product ID inside of that result, and it uses that product ID to construct a separate query, a second query, looking through product, saying, which product is the one for that particular ID? Give me all the details about that. And that's how it constructs that final result of products. Okay. Now let's zoom in on that second, or I should say that last query. That's kind of where the trouble lies here. And there's kind of 2 ways that it's problematic. First, it's not as safe as it could be. If you look at the query, I've copied it again here. It doesn't filter on store ID at all. Now, in this case, it's okay. It's safe. It happens to work out. The order was already chosen from the right store. And so this is its product, presumably also in the right store. But really, it'd be cool if all queries always had that protective filter on the tenant, on the store in this case. Just whatever queries active record is going to be sending, they have a protective filter. That would just be a nice thing to know. Then no matter how fancy my queries are and tricky and big, they're always going to generate queries that are safe. So safety is an issue. And then the second problem is actually it's not as fast as it could be. And this is a distributed database thing because it didn't seem bad. The SQL is just pulling some stuff as it should. However, what's happening is when we make this query, we're saying, okay, distributed database, give us products. I want product 7. We did not tell it is the specific tenant, the store, because the tenant determines the shard that it's going to be pulling data from. And the shard is known in the metadata to live in a certain node. So the query planner, given just this, has no idea where this thing is. All it can say is, well, we have products, and I know there are 32 shards. That's the default. And so I'm just going to ask each and every one. I'm going to spin up a whole new query called a task, our little fragment query that's specific to a shard, and send out 32, send them out to all the workers and say, do you have product 7? Now, 31 of them are going to come back and say, no, I have no idea. I don't have it. And one of them will be good, and it'll combine that information to give you the one. But it just didn't know where to send it. So we need to provide the query planner more information. So we've seen this, that using the standard active record with a distributed system like this and a multi-tenant system is not particularly as safe as it could be, and it's not even as fast as it could be. So rather than having you try and mess with active record, Django, we created some libraries for it. Now we're focusing on the active record Rails one right now. We called it active record multi-tenant. And here's how we'll pull it in to take our original example and make it work better. It doesn't really change the length of the code much at all. We just say bring in active record multi-tenant, and we also bring in composite primary keys, which we didn't write. It's another gem out there that'll give this capability because we wanted to match more closely the way uniqueness works and Now we can because the queries are scoped properly. But really the key thing is in each of these models, we added multi-tenant store. We're saying this model participates in a multi-tenant system and its notion of tenancy is a store, the store ID. With that in place, now we can execute queries inside of a context that's going to scope anything and everything that Active Record generates, any SQL. So what we do is we say multi-tenant, we started up with a particular store. As we said, we didn't care which one it was. We just picked the first store. We said, with this in mind, now everything is for that store, do these statements. And any queries inside of this section are going to be safe. Not only will they be safe and fast, as we saw, but they actually look a little simpler. Now I just say, go through all the orders, find the one who's most expensive, and then find the product for it. By saying all the orders, it's understood that it's all the orders just for this store. So I didn't even have to write as much code, and it works better. It's kind of win-win. If we look and kind of verify the queries it's making, just to see how is this safer, what is it doing? The first query is the same. It's grabbing the stores, pulling that first one out. Then once again, it's finding the orders for the store, the order that's most expensive. But here in the magic, the last one, it's pulling the product. Yes, it's saying product ID is 7. Here I'm not showing the number 7, I'm showing the substitution thing, but it's searching for a specific product ID. But it also put in a seemingly redundant filter on store ID equals 1, and that's where the protection and the speed comes from. You don't have to touch it, that's just the way it makes queries now. So it's great. And it's fast. And we can see how it's fast by looking, once again, asking the query planner, what are you going to do with this query? I say, explain this thing. This is the query I know that Active Record generated. And now the query plan is showing me task count is 1. It knows it only has to ask one question. And it knows exactly which worker to send it to. In this case, it's worker. So it just sends it to one place. The single machine sends the results back, and it's really fast. So now we've seen that the queries we've generated are safe and fast and easy to use. So go get them. We've created helper libraries for 2 application frameworks, popular ones, Django and Rails Active Record, and with others possibly down the line. They're all in the Citus Data GitHub organization for you to try out. Thanks for watching, and enjoy the rest of the Azure Cosmos DB Liftoff.
Hello, everyone. My name is Sudhanshu Vishodia. I'm a customer engineer with the Azure Cosmos database team at Microsoft. My role involves assisting customers implement highly scalable and performant applications in Postgres. In today's demo, I'm going to show you how you can build highly scalable IoT application with millions of devices on Azure, and why you should choose Azure Cosmos database for Postgres to build it. Before we move further, let me quickly brief you on what IoT is. IoT basically is a huge network of interconnected devices which are capable of transmitting data over the internet or private networks. Sensors, gadgets, appliances are some of the common examples. Let us first understand the characteristics of IoT devices. IoT devices typically require scalability, high throughput, high concurrency, and low latency. Since the IoT devices are growing at a very rapid pace, so while designing an IoT app, it becomes crucial to choose the right technology early, which can keep up the pace and allows the system to grow without affecting its performance over the time. The term heterogeneous basically means the ability to support a variety of devices from different manufacturers. Since the data generated for different devices could be different, and that is where semi-structured data sets comes into play. And we'll talk more about it in the coming slides. So why Azure Cosmos DB for Postgres? It's a great platform to build time series IoT application on Azure. To start with, you get a great performance in terms of ingestion, throughput, concurrency, and the millisecond response time for your read transactions. It offers you native support on sharding, which gives you the power to parallelize queries across the worker nodes. With smaller shards, you get better index and cache hit rate. For time series workload like IoT, the shards can be further broken into smaller subsets using range partitions on time. This will allow you to further prune the data for performance. Cosmos database for PostgreSQL also meets the scalability requirement of IoT workloads. Since there is no upper limit on the number of worker nodes that you can provision, which basically means you can scale it to the millions of devices without any problem. Also, it supports online rebalancing, so no more downtimes whenever you add new nodes to your cluster. It also allows you to store data for a variety of devices having different schemas together as JSON, JSONB type. This gives you a flexibility to store and query both structured and semi-structured data together without losing any of the SQL functionalities that comes with the relational databases like joins, lookups, indexes, foreign keys, etc. Cosmos database for Postgres also supports IoT applications which need geospatial data. Here is a reference architecture which explains the data flow of the events right from the point of their inception till the time they are consumed. The complete life cycle can be divided into 5 phases. First, the devices or the sensors will collect the information from their physical environments, and the series of events are transmitted over a network. Azure IoT Hub will then intercept the incoming events and route it to Azure Stream Analytics for further processing. IoT Hub do not process any data on its own and just act as a hub for bidirectional communication between your IoT application and the devices. Azure Stream Analytics query will help us in extracting the required data fields and implement filters, basic aggregations, and sample the events for business requirement before loading this data into Azure Cosmos database for Postgres. You can also use Azure Databricks or Kafka as an alternative to Azure Stream Analytics. Once the data is ingested in Cosmos database, all the complex data processing, the business logics can be implemented at this stage. The process data will then be used to build meaningful metrics and is exposed to the end users for action. For this demo, the data flow has been set up as explained on the previous slide, wherein we have already registered 1 million devices, including thermostats, coffee machines, and windmills on Azure IoT Hub. We have used IoT Hub device provisioning service to provision the devices at this scale. These devices are being powered by simulator program at the backend, which generates a throughput of roughly 45 million events. I'll repeat this one. These devices are being powered by a simulator program at the backend, which generates a throughput of roughly 45 billion events per minute. These events will then follow the Azure Stream Analytics route and be ingested into the Azure Cosmos database for Postgres. Similarly, read load is simulated using Postgres pgbench extension, and it runs the test with a variety of query patterns like single selects, cross-node selects, updates, and delete transactions. Azure Cosmos database for Postgres has been used as a target with 1 coordinator and 16 worker nodes. We have also developed a couple of Power BI dashboards. The first one tries to capture the meaningful metrics around IoT devices, while the other provides a snapshot of the database performance in terms of write throughput, scale, and the query response times. Let us quickly jump to the demo and show you how the data is modeled in Azure Cosmos database for Postgres. So let us first have a look at the cluster configuration. So for cluster configuration, I'm going to run a query on pgdist node here. As you can see, I have a total of 17 nodes here, out of which 16 are worker nodes and 1 is the coordinator node. So like I said, we are using a 16 worker node configuration for this test. In this demo, we are ingesting data into the events table. The table definition shows connection device ID, partition ID, ID as structured data, and payload, which is a JSONB type field for semi-structured data. Events with different data formats are being loaded as JSONB. Event processed UTC time is for tracking the time lengths. Additionally, we have also implemented partitioning on event processed UTC time to further prune the data for improved performance. Cosmos database for Postgres provides APIs to automate the time-based partitions. And here is one example wherein I'm using create time partitions functions to create the partitions in future. If you look at the index here, this index is created to improve the performance of the queries, which filters on event processed UTC time and the device type. If you have a look at the index carefully, you'll see the beauty of Postgres, wherein it allows to create composite indexes on a combination of structured and semi-structured data set from the JSONB field. So event stable here is distributed on device ID, which is the natural dimension for IoT workloads. At last, let's have a look at how event stable is sharded into multiple smaller chunks at the backend. For that, we can query Citus_tables. So as you can see at the backend, the main events table has been distributed into smaller chunks called shards. And if you look at the size of these, the first 4 partitions that we have already loaded, you see that we have already loaded around 4 terabytes of data into this table. So here is a dashboard which plots a few metrics around the events for different IoT devices that we have. So the first visual here plots a variation in average, minimum, and maximum temperature for different thermostats with respect to time in form of a line chart. So we have a similar graph here, coffee machine, which represents similar parameters. Here we have a graph for windmills. This basically represents the total number of rotations with respect to time. And these graphs, the good thing is that these graphs are being refreshed in a real-time basis. You can refresh the dashboard to get the latest feeds. You see, the dashboard has refreshed. In the second dashboard here, you can see we are ingesting at the rate of around 750,000 events per second into a table which has 15 billion events already loaded. The size of the table is roughly 4 terabytes, as I've shown you before. And with the kind of composite primary keys, the indexes that it has, and with all of that, we are still able to achieve a very good throughput on Azure Cosmos database for Postgres. On the other hand, if you'll see, the read load is being run at a concurrency of 200 users, and we are still able to achieve less than 10 millisecond response times for all of the different transactional queries that we are running, whether it is update, delete, the different variants of selects. The important point to note here is all the read transactions are running in parallel with the ingestion jobs, which is ingesting data into a table which is having 15 billion records in it. So you see that scale, that is just incredible. And this is what Azure Cosmos database for Postgres promised to deliver for building scalable IoT and time series applications on Azure. To summarize the talk, we saw Cosmos database for Postgres, capability to handle high ingestion and low latency workloads, how native data distribution helps in achieving the scale requirement required for IoT time series applications. We also saw how JSONB could be used to store data with different schemas from variety of IoT devices. And at last, the SQL expressiveness, which allows us to query both structured and semi-structured data together. With that, I'll wrap up this session, and I hope you would find it useful. Thank you.
And we are back. As with any talk from Joe Nelson, that was a great session. The active record multi-tenant Ruby gem really makes it easy to build multi-tenant SaaS apps on top of Postgres and Rails.
Yes, I really enjoyed Sudhanshu's session on building IoT apps, and I think it's really nice how JSONB supports, writing queries across like structured data or JSON data, and able to do like all of those full indexes with it. I think that's really, really cool.
Now remember, we are taking, if you're just joining us now, you may not know this, but we are taking your questions live. So feel free to use the chat and talk to our speakers and other engineers on our team.
Yes, and next up we have Principal Program Manager Nik Larin, who will talk about multi-region replication and disaster recovery with Azure Cosmos DB for Postgres.
And then Mark Heckler, who's a principal cloud advocate on the team, is going to show how to create Spring Boot applications using Azure Cosmos DB for Postgres. We think you're going to love that session too.
Yes, so let's watch.
Hello. Welcome to the Azure Cosmos DB Liftoff series. My name is Nik Larin. I'm an Azure Cosmos DB for Postgres product manager. Today, we're going to talk about scaling our distributed Postgres database in Azure, scaling reads across multiple Azure regions, and using Postgres cluster read replicas for disaster recovery. Before we begin, let me quickly go through the key terminology we use in our distributed Postgres. Postgres cluster may have two types of nodes, coordinator and worker node. Each node is a managed Postgres server with Citus extension running on its own virtual machine. Coordinator stores cluster metadata and is the cluster node that your application connects to as it would to any other Postgres database. Coordinator acts as a dispatcher for distributed queries and writes directing them to the right nodes in the cluster and aggregating read results coming from individual nodes before sending it back to the application. Worker node stores actual data in the form of shards, and shard is a Postgres table on a worker node that contains subset of rows for a given Postgres table. We talk about sharding when we need to distribute Postgres database, or in other words, divide data among the nodes by putting it in individual shards. Distribution column, also called distribution key, is used to assign table rows to specific shards. Choosing the distribution column for each table in your database is one of the most important data modeling decisions. It determines how data is spread across the nodes in a cluster and hence performance of the distributed Postgres. Now that we reviewed the key terms for distributed Postgres, let's take a look at the scale-out capabilities. The most fundamental ability of Azure Cosmos DB for Postgres is scale-out. You can start with a single node Postgres and shard your Postgres database by adding more nodes to the cluster in future. Let's take a closer look at what defines single and multi-node Postgres. A single node Postgres is what we offer in as a part of the Azure Cosmos DB is a robust and full-featured managed Postgres. It is built using native open-source Postgres. We support all major Postgres versions that are maintained by Postgres community. The major benefit of using native Postgres that is not a Postgres fork in our managed service is how fast we can deliver innovation in Postgres database engine and compatibility with rich Postgres ecosystems, including extensions. Then, our single-node Postgres offers a broad range of features that you may expect in a managed relational database service, from compute and storage scaling to high availability to network security options, including public and private access, to cross-region read replicas that we're going to talk more in this presentation, and more. One of the distinctive features of our single-node Postgres is ability to define data distribution model even before you need all power of multi-node cluster. To do that, you would need to select a column to be used as a distribution key and create distributed tables. That would define shards and rules for possible future multi-node cluster. Doing that is easy before you ingest significant amount of data into your Postgres database and makes your workload ready for future scale-out. So how exactly transition from single node to multi-node works? When you outgrow single node or simply need power of distributed Postgres, you can transition to multi-node Postgres in 2 steps without downtime. First, you need to add worker nodes. Once added, worker nodes are empty, so you need to move some data to these nodes. For that, you need to do so-called shard rebalancing that would move chunks of data to the worker nodes with 0 database downtime. Your application continues to work as before, as connection string stays the same, and all features that you configured before for your single node Postgres will continue to be there in the multi-node configuration. Once data is moved to worker nodes, your transition from single node to multi-node Postgres cluster is completed, and you can enjoy benefits of multi-node Postgres performance. Here's how transition works. On this slide, we're starting with a single node on the left that combines coordinator and worker node roles. We talked about data modeling on single node by choosing distribution column and creating distributed tables. Once done, it is just about adding worker nodes to your single node with few clicks in Azure portal and rebalancing shards, so that data is moved to the newly added nodes. On the left side, you can see a single node configuration that is transitioning to multi-node one on the right with 1 coordinator and 3 worker nodes. After transition to multi-node cluster, your application continues to connect to coordinator node for reads and writes with elevated performance delivered by multiple nodes. When your data and performance needs grow even further, you can keep adding worker nodes to your multi-node configuration with 0 downtime. Let's take a look at a live Postgres cluster that has outgrown single node Postgres and needs to become a multi-node one. While scale-out helps to keep growing your cluster with 0 downtime, all of it is happening on one cluster? What if you have a very demanding read consumer, such as hundreds and thousands of users refreshing their analytical dashboards? Cluster read replicas may help in this case. You would create a read replica cluster in the same or another Azure region and point those readers to that replica to offload reads from your primary Postgres cluster. You can create read replicas for single node or multi-node clusters. Let's take a look at what defines read replica clusters. First of all, it is a synchronous replication. It means the transaction can be committed on the primary Postgres cluster before it's replicated to all replicas. That improves write performance on the primary cluster, but also means that you have so-called replication lag on replicas that you would want to monitor using Azure Monitor metrics. Each read replica has its own connection string as well as certain configuration settings, such as compute configuration. It means that you can have a more or less powerful read replicas compared to your primary cluster, depending on the actual compute needs on these replicas. You can create up to 5 replicas in any supported Azure region. Last but not least, you can create read replicas for a read-write cluster, but you can create a replica for a replica or so-called nested replicas. In addition to read scalability, read replicas can be used for cross-region disaster recovery when you need to switch from your primary cluster to another one in case of region unavailability. Read replicas can also be used to move your Postgres cluster from one Azure region to another. Let's take a closer look at disaster recovery with read replicas. So a read replica in Azure Cosmos DB for Postgres can be promoted to an independent cluster available for reads and writes. You can break replication relationship between a read replica and its primary cluster at any time. As replication between primary cluster and its replicas is asynchronous, there is often replication lag that can vary across nodes in a cluster. To decide on whether you would like to promote specific replica to an independent cluster, you may check replication lag on all nodes in the replica cluster using Azure Monitor metrics. Once read replica promotion is initiated, it cannot be reversed and would take a few minutes to complete. Now let's take a look at what we discussed today. We talked about single node and multi-node Postgres clusters and how to transition from single node to multi-node clusters, how to set up read replicas of distributed Postgres database in different Azure regions, and finally we talked about how to use read replicas for disaster recovery. If you would like to learn more about Azure Cosmos DB for Postgres, use this short link. Thank you very much for your time.
Welcome to the Azure Cosmos DB Liftoff. This session is about Planetary Scale Postgres for Spring Boot apps, or as I like to call it, a fast and frictionless migration path for developers. My name is Mark Heckler. I'm a principal cloud advocate of Java and JVM languages with Microsoft. If you have any questions, comments, or feedback, I can be reached via email at markheckler@microsoft.com, or better yet, on Twitter at mkheck. I check email occasionally. I live on Twitter, so please reach out to me. My DMs are open as well. A bit about me. I am an architect and developer. I'm also obviously an advocate. I've also co-authored and authored some books, and you can check those out. Follow me on Twitter, and you'll find out more. I am a Java champion, Java 1 rockstar, Kotlin developer expert, and a licensed instrument-rated pilot. But that's enough about me. Everybody needs a hobby, right? And everybody needs to stay busy versus bored. So what's on today's agenda? We're going to be developing a Spring Boot application and connecting it to a local PostgreSQL database. And that's kind of meant to, in a small scale, mimic what is probably going on in a lot of our organizations, in which we have Spring Boot applications talking with and using external PostgreSQL databases on a local level or private cloud or what have you. We're then going to tackle one of the most difficult problems that developers face many times, migration to a much larger, more scalable, more resilient data store in the back end. And we'll be using Azure Database for PostgreSQL, or as I like to call it, Planetary Postgres. We're going to do all this, by the way, in under 15 minutes. What could go wrong? With that, let's code. We're going to start our project using the Spring Initializer, and we're going to use the standard build system of Maven, and we're going to use Java for our language, and the current version of Spring Boot, which is 2.7.4. We're going to change the group because why not? I can. And we're going to just call this our planetary Postgres application. And I'm going to use jar packaging because, after all, it's current day. Why not? And we're going to use Java 17 because it's the current LTS version of Java, but you have options once again. I'm going to bring in a few basic dependencies here so that we can create a web-based application. I'm going to be using JPA, the Java Persistence API, to access our database backend, and we'll use the Postgres driver to access Postgres, obviously behind the scenes. And then I'm going to bring in Lombok because I'm a lazy developer, but lazy in the good ways, right? Lazy when it counts, not in the bad ways. And we're going to further reduce our boilerplate code so that we can focus on the important things today and not just the extra stuff that we might have to deal with a lot of boilerplate. We don't want that. And I'm going to generate our project here, and we will save that. I'll just save that to my desktop, and we'll open it from there. And I find the zip file that we've downloaded with the project. We'll open that. And for today's coding, I'm going to be using IntelliJ. Now notice that, yes, I work at Microsoft, and I'm using IntelliJ on a Mac to develop Java code. And that's because Microsoft wants to be the ultimate destination, the best destination for your applications, your data, anywhere in the world, in the cloud. So whatever your toolchain choice, whatever your platform choice, whatever your language choice, it's all there. We're happy to help you have the best possible outcomes you can have. So with that, I'm going to launch in and just take a quick look at my build file, my pom.xml. And we see that we're using Java 17. We're using the current version of Boot 2.7.4. And we see our dependencies here that we included in our project. I'm also going to open up my application.properties, which allows me to provide some suitable defaults for a few values that we'll need in our application. So I'm going to define here our data source URL, and I'm once again going to be using JDBC and PostgreSQL, and I'm going to first access a local database, as I mentioned, and I'm going to be pointing that to a database I have up and running currently on localhost called Postgres. Clever, right? And I'm going to specify the username. And in this case, the username is just Postgres. And then I'm going to also specify the password. Please don't tell anyone, but I guess we all know that everything runs on caffeine anyway. So I guess it's not a big secret. And then I'm going to define one more thing, which is the DDL auto parameter for JPA Hibernate. And I'm going to set that to create drop. Now, this is a wonderful parameter to set for development, great for devs, for dev, not for prod, because obviously we don't want to create our table structures and when our application starts, and we don't want to delete them when our application ends in production. But for development, this helps focus on that developer first experience and get us up and running quickly and efficiently so that we can concentrate on the business at hand, which is to develop our application. Again, I'm going to keep this pretty simple based on our short time we have here together today, but I'm going to define a data class here for us to store the important things and retrieve them. So I'm going to set this as an entity. I'm going to define this as an entity, and I'm going to use Lombok to make this a data class. I'm going to also have Lombok provide a noargs constructor for me because JPA requires a noargs constructor in order to function properly. And I'm going to ask that Lombok provides us a required args constructor. Now, Lombok is a bytecode generator, so that allows us to keep everything nice and tight and clean for the demo. Some folks use it in production, some don't. But we're going to use it here today because that way I can focus on the key bits and not get bogged down once again in the boilerplate. And I couldn't think of anything else to save, so I'm just going to save some marks. You know, every demo needs some target. That's us. And I'm going to define our ID field here and ask that Postgres generates the value for that. And I'm going to make this a long value and just call this cleverly an FID. I'm going to specify the next couple of fields should be non-null. And non-null combined with this required args constructor annotation for Lombok means that Lombok will create a constructor with a parameter for each of the member variables indicated to have required values. In this case, we have first name and last name. So Lombok will create a constructor with just these two parameters. So I think that does everything that we need it to do for now. I'm also going to define an interface, a Mark repository interface, repository, and we're going to extend the defined CRUD repository interface that's in Spring Data. So we can store objects of type Mark with IDs of type long. And this is enough for Spring Boot's autoconfig to see this interface, extending a Spring Data interface, and create a proxy bean to allow us to interact with our table, with our database, in this case a Postgres database, and store and retrieve marks using a set of CRUD operations, create, read, update, and delete. And that's sufficient to get us up and running. I'm going to now create a bean so we can load some data into this and retrieve it and see that it's actually working. Just going to use a command line runner bean, and we'll say load mark data here, and we will load some marks. And I'm going to inject our Mark repository here so that we can use that once again to access our database behind the scenes. Command line runner is a functional interface with a single abstract method, and as such, since Java 8, we've been able to just specify that as a Lambda, which we're doing now. I'm going to use our repo that we're injecting, and I'm just, as a matter of good habit, deleting all values in case I've left anything in there before. And once again, this actually shouldn't be required, this delete all, because if we're doing a create drop, we shouldn't need it. But again, this is a good practice and habit to get into, so I'm going to continue with the habit. I'm then going to specify some marks to save to our data store, and I'll just do this again rather quickly. And I'm going to save maybe 2 or 3 of these. Let's go with 3. Why not? And we'll save these, and I'm actually going to bring those in as a list of. And of course, let's see, I'll go ahead and redo this. Some new marks. And there we go. So let's start off with Mark Brown. Mark Brown leads the charge with the Azure database for Postgres and Cosmos DB engine development back here at Microsoft. So Mark's kind of a celebrity in my eyes. He's also the host of Cosmos DB Learn TV. You've probably seen him. You've probably heard of him. And then I'll throw me in because, well, I'm here. Why not? And then I'm also going to bring in another Mark. Probably nobody's heard of this one, Mark Hamill. He's just kind of an up-and-coming actor nowadays, I hear. And then I'm going to just do a repo find all for each, and we'll just print this out to make sure we have working what we think we have working. It's always good to test, trust but verify. And I'm going to restart this or start this application, and we'll see what we get. So what should happen is we should open up a connection to Postgres, and we should save these marks, and then we should retrieve them and print them out. And of course, it works because things always go perfectly in live demos, right? Well, that aside. The next thing I'm going to do, because up to this point, this is just meant to simulate your normal Spring Boot development cycle. So you're using a local database, you're developing your application, you're iterating quickly, and you're getting things ready to go to production, but they're not there yet. So the next thing I'm going to do is tackle one of the hardest things about development work, which is migrations. Now, I do want to, just so we can prove what's going on here, do a couple of changes. Now, how do you get this to use a planetary scale Postgres? So I'm going to copy this, and instead of the data source we have here, I need to point to a planetary scale Postgres installation. The easy way to do that, since I already have things kind of set up, just in the interest of time, I've created an Azure database for PostgreSQL single server instance, and then I can go here to see my connection strings. And here we see the connection string for JDBC. Let me zoom in on that just a bit. And we see that we can grab that connection string and plug that in and use that. So I'm going to copy that to clipboard and go back to my IDE and just paste that in. Now you can see that there are some variables here that we need to provide values for, the database and of course the password. We're requiring SSL, so on and so forth. But we have all the basic pieces in place that we need. Now, I do want to do one more thing first, just in the interest of proving that we're doing what we say we're doing. I'm just going to get me out of here. I'm certainly not essential to this demo data. I'm here after all. And I'm going to add in another famous Mark. Well, We have Mark Brown, Mark Gaddis, and Mark Hamill now. 3 famous Marks. Mark Gaddis was a showrunner and contributor to BBC's Doctor Who and Sherlock. Don't know if you've heard of him, but probably so. And I'm going to, and that, by the way, I do that just so we can verify that things have switched, that we are going to be using Azure Database for Postgres. And I have an environment variable set behind the scenes, so you can't see my password. But what I'm going to do now is just go in and build our application here at the command line, and then I'll run it from the command line, and we'll see that everything, hopefully, will be connected to a much more scalable, resilient, robust version of Postgres running in Azure. So we got a hint of that right up there in the build. I'm going to go ahead and do a java-jar target, and we'll just run it from here and see what we get. And then, of course, everything works because, again, things never fail in live demos. We see that we have Mark Brown, Mark Gaddis, and Mark Hamill, and I don't think you can get any better than that. So with that, owing to our short time we have here together, I'm going to go back and finish up and share some resources that you might find handy. For starters, the repos. If you want to see what kind of scripts are necessary, which they're very small, very lean, but they are scripts that I use to create an instance of the Azure database for Postgres in Azure. And of course, I use the Azure command line interface, which I'll get to in a moment, but the scripts repo is there, as well as the demo repo for the Spring Boot application. You can kind of examine the dependencies and what I used. And maybe wonder why I didn't use something. By all means, that's where the bottom part comes in. If you have any questions, comments, or feedback, please reach me at my email or better yet on Twitter. The middle section is kind of the key, I feel like, because if you want to know more about Cosmos DB, aka.ms/Cosmos DB, if you want to know more about the Azure command line interface that I use for my scripting, it's there. You certainly have options. As you saw, you can go through the portal and go through and use the portal to create your Azure instances. You also can use other tools as well. I just am fond of scripting and the AZ CLI. With that, we're done. So good luck and go forth and Postgres.
And welcome back. We hope you enjoyed Nick's session on replication and Mark's session about Spring Boot.
Yes, I really loved how Nik showed users how you can create a replica in any Azure region, and just being able to take that replica and promote it to be like a primary cluster. I think that's a really good, useful feature.
And I think Mark's session was fun to watch too. He created that small Java app completely from scratch in 10 minutes, and then migrated it to run in Azure, in the cloud, of course. I also liked all the Marks he featured. He had Mark Hamill and Mark Gaddis and Mark Brown and Mark Heckler, and I got a kick out of that piece.
Yeah, no, we're getting close to the end of the event. Can you believe that? But just a reminder, okay, we're still taking your questions, so please, our team is here to answer questions and help you, so just use the chats.
And it's time for our last 2 sessions, and we're going to change things up a bit. Meredith Moore, who's a product manager on the Cosmos DB team, she's going to do a quick tour of Azure Cosmos DB for NoSQL. She's going to show you how you can get started for free using the new Try Cosmos experience, and so that you can try any of the database options in Cosmos DB.
Yes, and then we have our program manager, Estefani Arroyo. She's going to be giving us some tips about partitioning your NoSQL workloads and show you how you can optimize your workloads and use our new monitoring capabilities.
All right, let's take a look.
Yeah.
Hey everyone, my name is Meredith Moore and I'm a PM on the Azure Cosmos DB team. And in this session, we'll be discussing Azure Cosmos DB for NoSQL API, formerly the SQL API. I'll highlight some of the NoSQL API's unique capabilities before showing you how you can get started for free in under 5 minutes. So if that sounds good to you, what is Azure Cosmos DB? So commonly it can be described as a multi-model database service globally distributed with SLA-backed speed at any scale and availability. But for today's session, we'll define it as Microsoft's fast distributed database supporting both NoSQL and relational workloads at any scale. So let's dive in. Perhaps you're wondering what I mean by NoSQL. Well, NoSQL can be explained as non-relational and horizontally scalable. Let's explore this further, starting with horizontally scalable. Unless your workload's very small with a low amount of data and requests, your data will likely be stored on a number of different physical servers or partitions within something we call a container. Now in Cosmos, we abstract all this away, but under the hood, you're reading and writing data in and out of Cosmos across a cluster of servers. This is better known as scale out, and it's how we achieve horizontal scalability, enabling unlimited storage. So when you need more storage, we just add more servers to your cluster to give you what you need. And additionally, when you need more throughput than your clusters are capable of providing, we can add more servers and compute to meet your throughput requirements. The second feature to introduce is non-relational. So what does that even mean? You probably already know that when you work with relational databases, you can set relational constraints between the different types of entities in the database. This lets you do things like set up foreign keys between your entities and do join operations across your data set. Cosmos DB for NoSQL does not have relational constraints. And why is this so? So at a high level, it's because Cosmos is horizontally scalable, and your data will likely be spread across multiple servers, tens, hundreds, maybe even thousands, depending on your storage and throughput requirements. So technically, it's not impossible to enforce relational constraints across a cluster of servers, but doing so would have an enormous impact on the performance and availability of your database. And because Cosmos DB for NoSQL is designed to provide predictable performance, we do not provide a way to declare relational constraints. So now, is Cosmos DB for NoSQL suitable for relational workloads? Why, yes. If you think about it, most of the real-world use cases we're dealing with are more or less relational. But because Cosmos DB for NoSQL doesn't let you define relational constraints, we have to use different techniques to show how the entity types are related. The most important thing is that this is not the same as modeling data on a relational database. All of the best practices for common relational databases do not work with NoSQL, and many of them might even be anti-patterns. So now that you have a good understanding of NoSQL and that it's horizontally scalable, offering unlimited storage and throughput, and that it's non-relational, offering flexible schema, let's get started with using Azure Cosmos DB for NoSQL. So it's incredibly easy to start for free on a single instance and grow to any scale without changing your app. You can try out Cosmos DB for free for 30 days without any commitment using aka.ms/trycosmosdb, and you'll have the option to extend or upgrade within your trial period. So this is perfect if you just want to kick the tires a bit, maybe you have an app that you want to build, or you want to try out a hackathon project. So I'll demo for you how you can get started with sample data in just 5 minutes. So as I mentioned earlier, Cosmos DB is a multi-model database with support for MongoDB, Apache Cassandra, PostgreSQL, which enables open source developers to use PostgreSQL data in Azure Cosmos DB. And if I navigated here to others, I can select the table API for applications written in Azure Table Storage and the Gremlin Graph API. So I'm going to use the Cosmos DB for NoSQL API, and this is a document data model. A document can be any structured data type, but JSON's commonly used, and it's what's supported natively. So you can also use SQL syntax to query your items. All I need to start is to sign in with my Microsoft account. And if you don't have one, you'll be asked to create one. It only takes a few minutes, and you just need to use any email address you would like and create a password, or you can sign in with GitHub. The whole process takes about less than a minute. So as I mentioned earlier, Cosmos DB is a multi-model database with support for MongoDB, Apache Cassandra, PostgreSQL, which enables open source developers to use PostgreSQL data in Azure Cosmos DB. And if I navigated to others, I can select the table API for applications written in Azure Table Storage or the Gremlin Graph API. I'm going to use the Cosmos DB for NoSQL API, and this is a document data model. So a document can be any structured data type, but JSON's commonly used, and JSON's what's supported natively. You can also use SQL syntax to query your items. So all I need to start is to sign in with my Microsoft account. And if you don't have one, you'll just be asked to create one right away using an email address and creating a password, or you can sign in with your GitHub. The whole process takes less than a minute. So no long sign up, no credit card, no commitment. The account was created for me in seconds. So now I can go and open it up in the Azure portal where I land in Data Explorer. This is a tool I can use to interact with my data. And right away I can get started with some sample data, or perhaps I prefer to connect to my database, or maybe I want to complete one of our learning modules first. I'm new, so I want to start with sample data, and I launch Quick Start. And it's going to walk me through creating a database and how to use Data Explorer. So it's named my database, it's set my throughput, and since I'm just getting started, it's recommending to share the throughput across my containers I create within my database. And by selecting auto scale, it will automatically scale up to the max request units I've set, which is 1,000. I can change these configurations after creation, and there's a lot of helpful information about throughput and auto scale and request units in our Cosmos DB docs. So my container's named, and the partition key is set, and the partition key is the name of the property Cosmos DB will use to decide which logical partition my data should go to. So you can think about this as an address to route your data. Now I'm ready to get started. So within a minute, my database will be created. So now you have a mindful moment to relax, take a few breaths, or stretch while the creation is happening. Great, my database is ready. So I can view data under items. I can also view them using the filter function. And maybe I have my own data that I want to add. So this is where I can upload JSON. And this is where I can select to run a SQL query, or I can use the filter function. And remember that I said you can change the throughput configurations. Well, here's where you can set that. And this is the thing that we're going to cut out right here, so I'll just skip to the next one. So lastly, I can connect to my app using my connection string, or if I don't have an app, I can get started with a sample app using one of these languages here. And when I'm ready to upgrade or extend my trial, I can do so by selecting the upgrade banner, and I'll do that here in Overview. And I'll first need to sign in to my account or create a new Azure account. And then once I've done that and created my Azure Cosmos DB for NoSQL account, then I simply can find my connection string, paste that in here, and move my data over. So we can move all of your sandbox data into your production. So now you know how to create your own Azure Cosmos DB account with sample data in minutes. Please do so at aka.ms/trycosmosdb, and thank you so much and enjoy the conference.
Hi everyone, I'm Estefani Arroyo, and today I'll be going over Cosmos DB performance and cost optimizations with our new elasticity features. So some of the new elasticity features that we have going today is hierarchical partitioning, merge, burst capacity, partition throughput redistribution, and these features are all in preview today. So imagine our first scenario where we are Contoso, an IoT plant sensor company, or where our mission is to provide plants a long, healthy life. The data model for our company is we have information like light, sensitivity, temperature, sensor IDs, tenant ID, humidity, and soil moisture. So now let's look at what partitioning strategies we'd like for our company. In this case, we have option 1, where we can partition by tenant ID. A tenant ID could be something like a household or a greenhouse. Or option 2, we can partition by sensor ID, where a sensor ID is a particular sensor that's located within a plant. And finally, we have option 3, which is a synthetic partition key by tenant ID or sensor ID. So for option 1, where we have partitioning by tenant ID, in this partitioning strategy, it's actually pretty easy to query per tenant, where we can have a query something like select star from C where tenant equals 1. But what if we have one household that becomes rather large? There's a scenario where in Cosmos DB, we have a limit of 20 GB of data per logical partition. So if we partition by tenant ID and one household becomes very large, like a greenhouse, then all of our queries that is partitioned by tenant ID will be a cross-partition query and something that we don't want. Okay, now let's look at option 2, which is partitioning by sensor ID. Sensor ID is actually pretty good in terms of cardinality of IDs, but not great when looking at things like cross-partition when querying per tenant. Finally, let's look at option 3. This option is actually pretty good in terms of creating a synthetic partition key by tenant ID and sensor ID. This will actually avoid the 20 GB tenant limit that we were talking about, but really we're not able to query by tenant. And also we'd have to handle additional app logic to create these new synthetic keys. Here we now introduce hierarchical partitioning, which is a way to configure up to 3 levels of hierarchy for partition keys to further optimize your data and distribution to enable higher scale. With this new feature, you can now partition by level 1 tenant ID, and then you can further drill down by sensor ID. You can even drill down to a third partition, something like event ID. So with this new feature, you can now avoid the 20 GB per tenant limit. You can query by tenant by targeting a subset of partitions, and you can also query for sensor IDs given a tenant ID. Now let's say there's a new scenario where a portion of customers decide to emit data less frequently, and this can result in some seconds of idle throughput. Meanwhile, a sensor ID has suddenly started to emit more data and also results in a huge usage spike. And you know this spike is actually occasional, unpredicted across a lot of partitions. So with this particular feature, burst capacity, now you can take advantage of those idle throughput seconds and use them for any usage spike. So each physical partition can now accumulate up to 5 minutes of idle capacity, and this can then be consumed at a rate of 3,000 RUs per second. So typically all of these requests would be throttled, but now with burst capacity, we're able to handle those spikes. In the chart below, you can see that there is a section of unused capacity prior to 546, and then a spike of RUs that increase beyond the 1,000 partition limit. And then after some time, it scales back down. This is basically burst capacity working between that time frame. Next, we have merge. Merge is a feature in which, imagine you have a scenario where you're saving roughly 1 year of data, and then later realize that you actually don't need one entire year of data, you may just need 3 months of data. In this case, we can then delete 7 months of data, in which case you have some partitions that have data, and then a few empty partitions. This is called storage fragmentation. So let's look at throughput fragmentation. Let's say your customer decide to scale up to 40,000 RUs initially with 10K RUs per partition. Then you eventually realize you don't really need 40,000 RUs, so you want to scale back down to 4,000 RUs. What happens is that the throughput is distributed evenly across all partitions, leading to 1,000 RUs per partition. And so in this case, you're only able to scale up to 1,000 RUs per second. So with merge, you can now merge containers that have that fragmented throughput or fragmented storage, and you can now create into one physical partition to reduce the number of total physical partitions in place. And finally, we have partition throughput redistribution, where in one case, you may have one greenhouse and further households. In this particular scenario, if you only have one greenhouse and you have multiple household IDs with a couple different plants in there, a greenhouse can become a hot partition given that they have so many plants and sensor data. So if you know that you've partitioned by tenant ID and you have one hot partition, which will be consistently that one greenhouse, then you can look at this new feature called partition throughput redistribution, where you can redistribute your throughput across all partitions to help you better achieve performance without having to configure your overall throughput based on the hottest partition. Right, now let's go into a quick demo. So in this view, today we are in the Azure portal, and we've created a small demo on how to use hierarchical partitioning. So here we have partitioned on tenant ID and sensor ID. This is a synthetic key. And with this view, you can see we have data in terms of tenant ID, this synthetic key for tenant and sensor ID, some address information, humidity, and soil moisture. And then we can try to run a query where if we run a select star from tenant ID where temperature is greater than 60, you will see that this query actually takes about 12 RUs to run. Now let's look at running the same query, but with hierarchical partition enabled. So hierarchical partition looks something like this, where you have partitioned by tenant ID and then further partitioned by sensor ID. So if we run a similar query in this hierarchical partition data set, you will actually see that we have about 4.65 RUs, which is significant cost savings in terms of the amount of RUs. All right, so these are all of the 4 elasticity features that we covered today. All of these features are, again, today in the preview, and easily enable these features using PowerShell or CLI. And for more information on how to enable these features on your Azure Cosmos DB resources, please visit the links below, and you'll find how to enable the features and what criteria you must meet to enable them on. Thank you for watching, and have a fantastic rest of your conference.
Welcome back. So that's it. We're at the end of our event.
I can't believe it. 2 hours. For 2 hours, we've explored the announcement at Ignite 2022 for Azure Cosmos DB for PostgreSQL.
And we covered so much ground today. We dove into how Azure Cosmos DB for Postgres provides high throughput, high concurrency, limitless scale, and supports key workloads like SaaS applications and IoT.
So with the addition of Postgres to the Azure Cosmos DB service, you now have both distributed relational and distributed NoSQL options in Azure Cosmos DB.
And if you're game to give it a try, you can sign up today for the free trial to see firsthand how Azure's new Postgres offering can help you build high-performance cloud-native apps on Azure. You can get to the free trial at aka.ms/trycosmosdb.
I like free. So if you missed any part of today's sessions, don't worry, just visit us at aka.ms/liftoff. Thank you all for joining.
We did it.
Yeah.